Welcome to this lesson on the symmetries of a square. Imagine you have a square coaster sitting on your coffee table. If you close your eyes and a friend picks it up, moves it, and puts it back down, how many ways can they do this so it looks exactly the same? Today, we are going to answer that question and build a bridge between simple geometry and deep algebraic structures. Now that we have our square coaster in mind, let us define what these invisible changes actually are. In mathematics, a symmetry of a geometric shape is defined as a rigid motion that maps the shape perfectly back onto itself. A rigid motion simply means moving the object without bending, stretching, or breaking it. For a square, there are exactly 8 distinct rigid motions that work. 4 of these are rotations and the other 4 are reflections. Together, these 8 specific movements form a collection that mathematicians call a group, which follows specific mathematical rules when combined. Before we move on to the specific mathematical notation, let us see this with a concrete visual diagram. To keep track of our 8 movements, we label the 4 corners of the square with the numbers 1, 2, 3, and 4, starting from the top left and going clockwise. You can also see the dashed lines representing our mirror lines for reflections. The horizontal line is H, the vertical is V, and the 2 diagonals are D1 and D2. The curved arrow on the right shows the direction of our clockwise rotations. This labeled square will be our map for everything that follows. With our visual map established, let us look at the first set of movements, the rotations. Conceptually, these are movements that keep the square flat on the table while spinning it around its exact center. We denote a rotation by the capital letter R, followed by the angle in degrees. The most basic move is doing absolutely nothing, which we call R0. Next, we can rotate the square clockwise by a quarter turn, which is R90. We can also do a half turn, R180, or a three-quarter turn, R270. If we rotate by 360 degrees, we end up exactly where we started, which is physically identical to R0. Now that we understand the rotations, let us look at the reflections. Unlike rotations, which keep the square flat, reflections require the square to be picked up in three-dimensional space, flipped over, and placed back down. We use letters to represent the mirror lines. We have a horizontal flip, denoted by H, which swaps the top and bottom corners. We have a vertical flip, denoted by V, which swaps the left and right corners. Finally, we have 2 diagonal flips. D1 flips the square across the mean diagonal connecting the top left and bottom right, while D2 flips it across the other diagonal. These 4 flips complete our set of 8 symmetries. Having defined all 8 individual symmetries, we can now explore what happens when we combine them. The real magic happens through a process called composition. Conceptually, this means performing one symmetry and then immediately performing another. The final result is always equal to one of our original 8 single symmetries. We write this combination using a small circle symbol, which means followed by or composed with. It is crucial to note that we read this notation from right to left. If we write A composed with B, it means we first perform the movement B and then we perform the movement A on the result. Let us see how this works mathematically. Before we move on, let us see this composition with a concrete example. Suppose we want to find the single equivalent symmetry for H composed with R90. This means we first rotate the square clockwise by 90 degrees and then we flip it horizontally. To do this, we will track the positions of the corners 1, 2, 3, and 4. We write our starting square as a simple matrix where the top row is 1 and 2 and the bottom row is 4 and 3. First, we apply the 90-degree rotation. Every corner moves one spot clockwise around the perimeter. The 4 moves up, the 1 moves right, the 2 moves down, and the 3 moves left. Continuing from our rotated state, we now apply the horizontal flip, H. A horizontal flip acts like a mirror placed across the middle of the square, swapping the entire top row with the entire bottom row. So the row containing 4 and 1 moves to the bottom, and the row containing 3 and 2 moves to the top. Now we look at our final arrangement and ask which single move from the starting position would have created this exact pattern. The 3 and 1 have swapped places while the 2 and 4 remain in their original diagonal spots. This is exactly what the main diagonal flip, D1, does. Therefore, rotating by 90 degrees and then flipping horizontally is physically identical to just flipping once across the main diagonal. So we have proven that H composed with R90 equals D1. This brings us to an important question. Does the order of operations matter? In basic arithmetic, 3 times 2 is the same as 2 times 3. We want to test if this commutative rule holds true for the symmetries of a square. To prove this, we will reverse the order and evaluate R90 composed with H. We start fresh with our standard untouched square matrix. This time, our first operation is the horizontal flip, H. Applying this directly to the starting square swaps the top row, 1 and 2, with the bottom row, 4 and 3. This gives us our intermediate flipped state. Now we take this intermediate flipped state and apply the second oscillation, which is the 90-degree clockwise rotation. The rotation pushes every number 1 position clockwise around the perimeter. The 1 moves up to the top left, the 4 moves over to the top right, the 3 moves down, and the 2 slides over to the bottom left. We now compare this final state to our original untouched square to identify the single equivalent move. We can see that the 1 and 3 are in their original diagonal positions, but the 2 and 4 have swapped places across the other diagonal. This specific transformation is exactly the result of the second diagonal flip, which we denote as D2. This brings us to the final conclusion of our proof. We just found that R90 composed with H results in the diagonal flip D2. However, in our previous example, we saw that H composed with R90 resulted in D1. Because D2 is not the same symmetry as D1, we have proven that the two compositions are not equal. In mathematical terms, we say that the group of symmetries of a square is non-abelian. This simply means the order in which you perform the actions completely changes the final outcome. You must always pay strict attention to the sequence of operations when dealing with geometric transformations. Now that we have used these matrices and proven the non-abelian nature of the square, let us understand why this matters in the real world. Understanding the symmetries of a square might seem like a simple puzzle, but it is actually the foundation of group theory, which is a massive pillar of modern mathematics and science. In chemistry, the symmetry of molecules determines how they react with light and other chemicals. A molecule shaped like a square will behave according to these exact 8 rules. In physics, symmetries dictate the fundamental conservation laws of the universe, such as the conservation of energy and momentum. Even in computer science, algorithms that manipulate 3D graphics rely heavily on tracking these exact types of rigid motions. We have covered a lot of ground today, so let us review the most important ideas. First, we learned that a square has exactly 8 distinct rigid motions, consisting of 4 rotations and 4 reflections. Second, we saw that we can combine these motions using composition, and the result is always another motion from our original set of 8. Third, and most crucially, we proved that the order in which you combine these motions changes the final result, demonstrating a non-commutative or non-abelian mathematical structure. Mastering this simple geometric example provides the perfect stepping stone into the abstract world of group theory. You have done a great job following along with these abstract concepts.